Hello students, welcome to another tutorial on static equilibrium. In this video, we look at how to determine the force that is needed to topple a person of a given weight who is standing vertically upright. Now, we are given the radius that we have to look at. Now, let's just try to picture this question and how we can approach it. So we're given the height, the 1.5 meters. So this is the height from the pivot, the point we're going to consider as the pivot, to where the force is being applied. So let's take this point to be our pivot. So this is our pivot. Now, what we're looking at is, or what the 1.5 is for, it is the vertical height from that point up to where our pivot is. So notice that this is up to where the force is being applied. Now, if we look at these two, they are already perpendicular. So it kind of works when we can use this 1.5 multiplied with this force to get the torque. So if we consider the same point as our pivot, then we see that the turning here, so if we take this as the turning one, we notice that it is an anti-clockwise rotation, and it can be obtained by multiplying force, the F we're looking for, times that 1.5, that height, which is the perpendicular distance from the pivot. Now, the next thing that we have to look at is the second force that is acting on this object, which is the weight of this person. So if we go back to the question, what we're given is the mass of the person, which is 65 kgs. So from there, we see that we can easily get the weight by multiplying the mass and g. So this will give us what the force is due to the weight. There's going to be a downward force. Now, in this case, since we have a downward force, the distance that we're going to use is going to be from the pivot going until when we reach there, the force, which is the weight in this case. And again, we see that this distance, not at the distance we picked, it is a one such that it is perpendicular to the force in consideration. So in this approach, we're kind of making sure that the distance gets to be perpendicular to the force, instead of the other approach where it is the force we make perpendicular to the distance. So in this case, we're going to use the radius, which is 0.1 in meters. So to obtain that, what we see is we have torque 2. So torque 2 is due to the weight. We see that it's W, the weight, multiplying the radius R, which is, let's keep it like this for now. So how do we get W1? It is the weight, which is mg times R. So this gives us what torque 2 is. Yeah, so by definition or by formula. So when we substitute now, the mass in this case is 65 kg, G is 9.8, and then R in meters, that is 0.1. Okay, so once we've got this, we can now look at what we have to do. Now, the idea here is we want to find what the toppling force is. Now, what is this force? Well, it has to be a force such that the anti-clockwise, because in this case, the weight is kind of acting, causing a rotation in this manner. So it is a clockwise rotation, while the force which is being applied is an anti-clockwise rotation. So just before this gets to be toppled over, or for this system to topple over, the anti-clockwise moments kind of have to match the clockwise moments. Let's say you first have a force being applied less than such that when you multiply it with the height, that 1.5, the product you get is less than the clockwise moments. You see that definitely the anti-clockwise moments tend to be more effective. So because of that, the system does not get to rotate in the anti-clockwise manner. In this case, we want to find the force which is sufficient enough to cause rotation in the anti-clockwise direction. And such a force has to be such that when we multiply it with the 1.5, it gives a product which is slightly, or which is actually greater than the product of the weight times the R. Okay, now that is what we want. So as soon as they become equal, as in the anti-clockwise and the clockwise, once they become equal, then we're saying we've reached equilibrium. But then for it to topple over, it has to just be about greater than that, as in the T1 or the torque one, the anti-clockwise one, has to just surpass the clockwise one. So the critical thing is to find a situation in which they are equal. We can still use the sum. We can still say sum of the torques is equals to 0. If we take anti-clockwise to be positive, then we have torque 1. And clockwise to be negative, then we have torque 2. They should sum up to 0. So we see that the situation we're looking for is when torque 1 is equivalent to torque 2. So in the perform our substitution, what we have is F multiplying 1.5 equal to, and then we look at what torque 2 is, that was 65 multiplying 9.8 multiplying 0.1. So from here, we see that when we divide both sides by 1.5, we get F as 65 by 9.8 by 0.1 divided by 1.5. And this reduces to give us F as 42.5 newtons. Now, this force that we get, it is just the force that is needed to once F assumes this value, then we see that the clockwise moments and the anti-clockwise moments become equal. If force just exceeds this value, even just a bit, then the anti-clockwise moments take effect. The object starts to topple in the anti-clockwise direction. So this is the minimum force that we need for us to move in the direction where the object, or the person in this case, starts to rotate in that direction. Of course, the assumption here is that the person does not slide when this force is applied. The person remains mounted or rooted vertically, and then the only force that is, as in, there is no motion as you push the person doesn't slide on the surface where he's standing. Okay, so we found this force that is needed, F. Now, the second question, if we go back to it, what they're now saying is, explain why the stability of a person against a toppling force is increased by spreading the legs. Now, to get a clear picture of what is happening there, all we're saying is, initially, you have a person who is, I'm just drawing a weird shape here. So what we have is, let's say this side you have the legs. So currently, or in the initial situation, this is what we have. So look at the diameter here. Now, if the legs are spread, notice that what will happen is that now what we have is, we have something like this. Now, what will happen? The two things that we have to consider. First and foremost, the center of weight. The center of mass in here. So the center of mass kind of reduces a little bit, because this initially was going up to that level, as in the height from here to where the center of mass is, but now it has reduces. And we know from elementary physics back in high school that the lower the center of weight or the center of mass, the more stable an object is. So if in the first case, this object was going up to that level, then what we expect is, by spreading the legs, the height kind of reduces a little bit. So the center of weight has been lowered. So lowering the center of mass implies that the object becomes more stable. Now, one key concept that we're going to concentrate on is the issue of the surface area. That's the second thing that kind of influences the stability of an object. So the first one is the position of the center of, so let's just say the center of mass, Cm. So the lower it is, the closer it is to the surface of the ground, the more stable an object is. But this is what we want to concentrate on, the base area. So here now, what we're saying is the greater the base area, the more stable an object is. Now, why is it so? Let's look at the turning effects. So, or if you recall what we looked at in the previous case, we had torque 1 equivalent to torque 2. Now, let's look at how we obtained torque 2. So torque 2 was the one due to the weight of the object. We had the weight multiplying R. But the thing is, if the person spreads the legs, then we kind of mess around with this R. Because in the first case, R was just this small distance. Let's use rate for this. R was just this small distance from here to there. But by spreading the legs, now notice that the point about which the object is rotating is somewhere there. Now R becomes from here all the way up to where the weight is acting. So the weight is acting still along that path. So we observe that in this case, R has increased. So because R has increased to something which is a little bit more, the product here, when you multiply R and W, becomes larger. So because the clockwise moments, talk towards giving us a clockwise moment, because the clockwise moment has increased, now what you should realize is now you also need the anti-clockwise moments. They will have to be a little bit more. They'll have to increase so that they match that clockwise moment that you have. Now, the only way that can happen is by increasing the force. So the force that you'd have to apply now to match the clockwise moments would have to be more than what you applied in the first case. So I hope that's clear. So spreading the legs means that the radius or the distance from the pivot to where the force is acting gets increased. And once that is increased, the product, when you multiply it with the weight, since the person still maintains the same weight, when you multiply that distance with the weight, which is constant, the product becomes greater. So the clockwise moments become greater. And since they're greater, it implies that the anti-clockwise moments, which will be needed to balance those, will now be also greater. They'll have to be more than what we had initially. And the only way we can get that is by applying more force. So that's the key thing that we have to look at. Now, let's quickly go to the third question, the last one. Now, for the third question, what they're saying is calculate the force required to topple a person of mass 70 kg standing on his feet spread 0.9 meters apart. Assume the person does not slide. Now, to work out this, apart from the conditions stated here, we're going to assume also that the change in height when the person spreads their legs is minimal. So what that means is we're going to assume that the height here and in this case is going to be the same. But of course, in practicality, what you know is that, of course, the height is not going to be the same. Spreading the legs implies that the height kind of reduces a little bit. But here we're going to assume that that reduction is very small, such that we can ignore it. So we're going to take height to be constant. So what we want to focus on is what does the increment in the radius, how does it affect the force that we need, F, in this case? So if the 1.5 is maintained, as in the first case, but the only thing that has changed is the force. So of course, the one difference between this question and what we had at first is, in the first case, we used 65 as the mass. In this question, what we are being asked to work with is 70 kgs. So I'll leave it to you guys to also try working this out with 65 kg and observe that the force that you're going to end up with is going to be greater than the force that we ended up with in this scenario. So I'll leave you guys to try out that. Let's work out the current scenario that they've pictured for us. So again, torque 1, as you've seen, it's F. We are still maintaining 1.5, but torque 2, remember torque 2 we had the weight multiplying R. But now if we go back to the question again, what we're being told is the person spreads the legs so that they are 0.9 meters apart. So if what we have is 0.9 meters apart, what this only means is the diameter from the edge to the far edge is 0.9, implying that the radius is half 0.9, which is 4.5 meters. So see that the radius has increased. Initially had 0.1, and then now you have 0.45. So when calculating torque 2, the clockwise moments, what we have is the 70 kg multiplying the 9.8 by the increased radius, which is 0.45. So again, I'm leaving it to you guys to try out when the mass is the same as that 65 we had in the first case, so that you observe how the force will change. Okay, so once we get this, we can again use the sum of the torques. Not torque 1. Sum of summation of the torque should equal to 0. So torque 1 is anti-clockwise to positive. Torque 2 is clockwise, negative, equating to 0. So this implies that torque 1 is equal to torque 2. This is the situation we are working with again. So from here, this is F1, not F1, F multiplying 1.5 equal to torque 2, which is 70 by 9.8 by 0.45. So from here, F is equal to the 70 by 9.8 by 0.45. So we divide this side by 1.5, and then what we get is F is equals to 205.8 newtons. So this is the force that that we'll get. So again, this is kind of different, of course, because it's not only the radius which has changed here. The mass that we're given this time around is 70 kgs. Now you guys can try it out if this was maintained to be 65. It's a minor detail, but you should also be able to get a force which is greater than the 42.5 newton we had in the first case. So, but of course we can still conclude from here. The force that we need this time with the legs spread is much larger. We now need 205.8 newtons to topple this person. But when the legs were close together, when the radius was 0.1, the force needed for someone of 65 kgs was just 42.5. The difference is quite huge. Okay, so I hope you guys were able to follow how to work this one out. Just kind of a short video. I hope you guys will find this helpful. So as you prepare for our next tutorial, this is the question that we are going to work on in our next tutorial. You guys can try it out in readiness. It's not something very complicated. It's something easy. So I'll urge you guys to try it out before watching the next video. So the idea here, there is a diagram that that is supposed to be shown here, but basically all that you have is a leg. Let me just draw this as an object. Yeah, that simplifies everything. So ideally, what you have is something like this. And then at the far end, we're assuming this is horizontal, of course. Then at the far end, we have something tied up here. And then we have a mass that is suspended there. Okay, so we have a mass that is suspended at the far end. Okay, yeah, so we have a mass that is suspended somewhere here. And then this mass is given. So we have some pulley here. The next thing that what you're being told is somewhere here we have the center of gravity. So that is the CG. And then apart from that, at the hip, at the far end, we have the hip joint. Then what are being given here are the distances from the hip joint to the center of gravity. And that is given somewhere here. That's 35 centimeters. And then the next limit is given is from the hip joint to where the force is being tied. So that is somewhere here, and this is 78.0 centimeters. So yeah, this leg, of course, there is some plaster. So let's color that a little bit. So there's some plaster which is there. So ideally we're saying this part of the leg is covered in plaster, and then we're given the mass of the plaster leg altogether. So that is basically all that you have to take into account when working out this problem. Really, you should be able to see the forces that are acting here. The ideas are the same. I hope you guys will find this very easy to work out. But of course, you can always check out the next video as I demonstrate how to work out this question. Otherwise, that is all for this tutorial. I hope you guys found this helpful. We'll see you in the next tutorial. This was your tutor.